In today's digital landscape, where privacy, security, and unrestricted access to information are more important than ever, virtual private networks play a central role in protecting users and organizations alike. In this video, we're going to take a deep and detailed look at OpenVPN 2.7, exploring what it is, how it works, what's new in this version, and why it matters for system administrators, developers, businesses, and everyday users who care about secure communication over the internet. To begin with, OpenVPN is an open source VPN protocol and software solution that enables secure point-to-point or site-to-site connections. It uses advanced encryption technologies to create secure tunnels over potentially insecure networks such as the public internet. The core idea behind any VPN is to establish an encrypted tunnel between a client device and a server so that data traveling between them cannot be easily intercepted, modified, or monitored by unauthorized parties. OpenVPN has been one of the most trusted and widely adopted VPN technologies for many years, known for its flexibility, configurability, and strong security model. Version 2.7 represents an important step in the evolution of this software. While it builds on the solid foundation established in previous versions, it also introduces improvements in performance, security, usability, and compatibility. For administrators and developers who rely on OpenVPN in production environments, understanding the changes in 2.7 is essential to making informed upgrade decisions and ensuring smooth deployment. Let's start by reviewing how OpenVPN works at a fundamental level. OpenVPN operates in either client-server mode or peer-to-peer mode. In client-server mode, remote users connect to a central VPN server. The client software on a user's device initiates a connection to the server, negotiates encryption parameters, and establishes a secure tunnel. In peer-to-peer mode, two endpoints connect directly to each other using similar encryption and authentication mechanisms. The software uses SSL and TLS protocols for key exchange and authentication. This means that before any secure tunnel is created, both sides authenticate each other using certificates, press-shared keys, or username and password combinations. Once authentication succeeds, a secure channel is negotiated using strong cryptographic algorithms. Data packets are then encapsulated inside encrypted packets and transmitted through the tunnel. One of the reasons OpenVPN has remained popular is its flexibility. It can operate over UDP or TCP. UDP is often preferred for performance because it reduces overhead and avoids some of the latency issues associated with TCP over TCP tunneling. However, TCP mode can be useful in restrictive network environments where only certain types of traffic are allowed. By running over TCP, OpenVPN traffic can sometimes pass through firewalls that block other protocols. In version 2.7, several refinements have been made to improve protocol handling and compatibility with modern operating systems and libraries. Over time, cryptographic standards evolve, and older algorithms become deprecated or considered insecure. OpenVPN 2.7 reflects these realities by aligning more closely with current best practices in cryptography. One major area of focus in 2.7 is improved support for modern TLS libraries and enhanced handling of cipher negotiation. Cipher negotiation determines which encryption algorithms will be used for the data channel and control channel. In earlier versions, configurations sometimes required manual specification of ciphers to ensure compatibility. In 2.7, improvements have been introduced to streamline negotiation and reduce the likelihood of mismatches between client and server configurations. Another important development in 2.7 is related to Data Channel Offload, often referred to as DCO. Data Channel Offload is a feature designed to move part of the data processing workload from user space into the kernel. Traditionally, OpenVPN operates primarily in user space, which means packet processing happens outside the operating system kernel. While this provides flexibility and portability, it can introduce performance overhead. With DCO, certain data channel operations can be handled more efficiently, reducing CPU usage and increasing throughput. This is particularly beneficial in high-performance environments, such as data centers or enterprise gateways handling large volumes of traffic. Performance improvements are not limited to DCO. OpenVPN 2.7 also includes optimizations in memory management, buffer handling, and the internal state tracking. These changes may not always be visible to end users, but they contribute to a more stable and efficient system under heavy load. Security is, of course, a top priority for any VPN solution. Version 2.7 continues the project's commitment to strong encryption and secure defaults. One trend in recent years has been the deprecation of older, weaker cryptographic algorithms. OpenVPN 2.7 reflects this by encouraging the use of more secure ciphers such as AES and ChaCha20-Poly1305. These algorithms provide authenticated encryption, meaning they ensure both confidentiality and integrity of data in a single operation. The handling of certificates and authentication mechanisms has also seen refinement. Certificate verification is a critical step in establishing trust between client and server. Misconfiguration can lead to vulnerabilities such as man-in-the-middle attacks. In 2.7, improvements to certificate validation and clearer error reporting help administrators diagnose problems more effectively and maintain secure configurations. Another area where 2.7 brings value is improved logging and debugging capabilities. For administrators managing complex deployments, clear and detailed logs are essential. When a connection fails or behaves unexpectedly, logs provide insight into what went wrong. The updated version enhances log clarity, making it easier to trace issues related to TLS negotiation, cipher selection, routing, or authentication. OpenVPN 2.7 also strengthens compatibility with modern operating systems. As operating systems evolve, they introduce new networking, APIs, security models, and kernel interfaces. The 2.7 release ensures better integration with recent versions of Windows, Linux distributions, and other supported platforms. This includes more reliable handling of virtual network interfaces, routing table updates, and DNS configuration. On Linux systems in particular, integration with kernel networking features has been improved. With the addition of Data Channel Offload modules, administrators can take advantage of kernel-level acceleration where available. This can significantly increase throughput and reduce latency. Especially on servers equipped with modern hardware, Windows users benefit from updates to driver support and improvements in the tap and ton interface handling. Reliable virtual adapters are essential for proper VPN operation. Any instability in these components can cause connection drops or routing issues. By refining driver compatibility and modernizing interface management, version 2.7 helps ensure smoother operation on contemporary Windows systems. Another noteworthy enhancement involves configuration file handling. OpenVPN uses text-based configuration files that define parameters such as server address, port, protocol, certificates, encryption algorithms, and routing rules. In complex environments, these configuration files can become lengthy and intricate. Version 2.7 improves parsing, robustness, and error reporting, making it easier to detect configuration mistakes before they cause operational issues. Backward compatibility is always a concern when upgrading to a new version. Administrators often need to ensure that older clients can still connect to updated servers or vCVA. OpenVPN 2.7 is designed with compatibility in mind, though it may require careful configuration if legacy ciphers or deprecated options are in use. Because this upgrading both server and client to 2.7 yields the best results in terms of performance and security. In enterprise environments, centralized management is crucial. OpenVPN can be integrated with authentication backends, such as LDAP, Radius, or Active Directory through plugins and scripts. While 2.7 does not radically change these integration mechanisms, it enhances stability and ensures compatibility with modern authentication frameworks. This makes it a solid choice for organizations that require secure remote access for employees and contractors. From a network architecture perspective, OpenVPN 2.7 continues to support both rooted and bridged configurations. In rooted mode, clients receive virtual IP addresses and traffic is routed between networks. In bridged mode, clients appear as if they are on the same local network segment as the server. Each approach has its use cases, and 2.7 maintains flexibility in supporting both models. Site-to-site VPN deployments, where entire networks are connected securely over the internet, also benefit from the performance and stability improvements in this release. For businesses connecting branch offices to a central headquarters, efficient and reliable VPN tunnels are essential. Reduced CPU usage and improved throughput can translate into better application performance for end users. Security hardening in 2.7 also includes more secure default behaviors. Over time, best practices evolve, and what was once considered acceptable may later be deemed insufficient. By updating defaults to align with current standards, the software helps reduce the risk of misconfiguration. However, administrators must still carefully review configuration files when upgrading to ensure that all required options are explicitly set. Another aspect worth discussing is IPv6 support. As IPv6 adoption grows, VPN solutions must handle both IPv4 and IPv6 traffic seamlessly. OpenVPN 2.7 continues to enhance dual-stack support, ensuring that clients can route IPv6 traffic through secure tunnels when configured to do so. This is increasingly important as more networks and services become IPv6. DNS handling is another critical component of VPN functionality. When connected to a VPN, clients often need to use internal DNS servers to resolve host names within a private network. Incorrect DNS configuration can lead to leaks, where DNS queries bypass the VPN tunnel. Version 2.7 improves DNS push and configuration handling, reducing the likelihood of such issues and enhancing privacy. Let's also talk about scalability. In large-scale deployments such as VPN providers serving thousands of concurrent users, efficient resource management is key. Every connection consumes memory and CPU resources. Optimizations introduced in 2.7 help reduce overhead per connection, making it more feasible to scale without excessive hardware requirements. From a developer's perspective, the 2.7 release may also include refinements to the code base that improve maintainability and future extensibility. Clean, well-structured code is easier to audit for security vulnerabilities and easier to extend with new features. Open source projects benefit greatly from community contributions, and a well-maintained code base encourages participation from developers around the world. Documentation is another area that evolves alongside the software. Clear and up-to-date documentation helps users understand new features, deprecated options, and recommended practices. While not always highlighted as a technical feature, improved documentation in the context of 2.7 can significantly enhance user experience and reduce configuration errors. In practical terms, upgrading to OpenVPN 2.7 typically involves installing the new package on servers and clients, reviewing configuration files for deprecated options, and testing connections in a controlled environment before full deployment. It is always recommended to back up existing configurations and certificates before making major changes. Testing in a staging environment allows administrators to catch compatibility issues without disrupting production traffic. For home users who run their own VPN servers, 2.7 offers the benefits of improved security and performance without requiring deep technical expertise. Many home routers and firewall appliances that support OpenVPN may eventually incorporate this version, providing users with enhanced capabilities through firmware updates. Cloud environments are another important context. Organizations increasingly deploy VPN servers in cloud infrastructure to enable secure access to cloud-hosted resources. OpenVPN 2.7 feet seconds performance enhancements and compatibility improvements make it well suited for virtual machines and containerized deployments in cloud platforms. Efficient resource usage is especially important in cloud settings where costs are often tied to compute and bandwidth consumption. In terms of monitoring and observing, 2.7's improved logging can be integrated with centralized logging systems. By forwarding logs to monitoring tools, administrators can track connection statistics, detect anomalies, and respond quickly to potential security incidents. Enhanced clarity in log messages simplifies the process of correlating events and identifying root causes. Let's not forget about compliance. Many industries are subject to regulations requiring strong encryption and secure remote access. By supporting modern cryptographic standards and encouraging secure defaults, OpenVPN 2.7 helps organizations meet compliance requirements related to data protection and privacy. Another subtle but meaningful improvement in newer versions is the gradual removal of legacy features that are no longer considered secure. While this can sometimes require configuration updates, it ultimately strengthens the ecosystem by reducing reliance on outdated mechanisms. Security is a moving target, and continuous evolution is necessary to stay ahead of emerging threats. When comparing OpenVPN 2.7 to alternative VPN protocols, it's important to understand its strengths. It is highly configurable, widely audited, and supported across numerous platforms. While newer protocols may offer simplicity or performance advantages in certain scenarios, OpenVPN remains a robust, mature solution with a long track record. In summary, OpenVPN 2.7 builds upon years of development and real-world deployment experience. It enhances performance through features like Data Channel Offload, strengthens security by aligning with modern cryptographic practices, improves compatibility with contemporary operating systems, refines configuration and logging mechanisms, and continues to provide the flexibility that has made OpenVPN a trusted solution worldwide. For anyone considering an upgrade, the key steps involve reviewing release notes, auditing existing configurations, testing in a non-production environment, and ensuring that both clients and servers are updated consistently. With careful planning, the transition to 2.7 can provide tangible benefits in security, stability, and performance. As we conclude this in-depth exploration, it's clear that OpenVPN 2.7 is not just a minor incremental update, but a meaningful refinement of an already powerful VPN solution. Whether you are a network engineer managing enterprise infrastructure, a developer integrating secure connectivity into applications, or a privacy-conscious individual running a personal VPN server, understanding the capabilities of this version equips you to make informed decisions about your secure networking strategy in an increasingly interconnected world.